In the last video, we looked at finding the optimal solution or solutions to linear programming problems. When we were looking at the decision variables x and y, they often come up to be fractional answers. So x might have been 3/4, y might have been 5/8. What we're going to do in this particular video is look at integer solutions. So you can see integer solutions as an additional constraint. An example of this might be if we're hiring coaches. If we want large coaches and small coaches, quite clearly we can't hire 3/4 of a coach. We can't hire 5/8 of a coach. So what we're doing is looking at now the decision variables that will give us integer solutions. We've got two particular methods by which we can do this, and we're going to focus on both of them as we go through a basic problem. So if we look at this question here, it says solve the following linear programming problem given that integer values are required for the decision variables. So remember, decision variables, x and y are our decision variables. So what we've got is now, this is our objective function. So we want to maximize 3x plus 2y. So here's our objective function, maximize 3x plus 2y, subject to these constraints. If this means nothing to you, please go back and watch some of the videos before, as this is all covered in those. So let's have a look at the first one. X plus 5y has got to be greater or equal to 10. 3x plus 4y has got to be less or equal to 24. 4x plus 3y is less than 24. And x and y are both going to be 0 or more. Okay, let's just move this over just a sec so we can squeeze that on. There we go. Right, so let's look at some scales. We've got now our xy coordinate axis. We know x and y are greater than 0, so I can put my origin down here. So let's grab up now the coordinate axis, and we'll put that like so. And then we'll come across, and now I'm going to choose some values. So if we consider this one, y would be 2 when x is going to be 10. We've got now this one, what's 24 divided by 3? That'll be 8, and this will be 6. This one is going to be 6 and that one will be 8. So from here I'm just going to do a 10 by 10 grid, and that's just looking ahead at my values there. Again, this was covered in the last video. So let's do this right here. So that's 5 and that's 10. Okay, down this way we will go 5 and we will go 10. So let's write on here now 0, that's the origin. This is the y-axis, that's going to be 5, that's going to be 10. We're going to have 5 and we're going to have now 10. So let's put our first one on. X plus 5y is going to be greater or equal to 10. And again, let's write this up. So let's just put it here. So that'll be my first constraint. And if I now set the x to be equal to 0, what we'll have is 0, 2. If I set the y equal to 0, we will have now 10, 0. That will allow me now to graph this line, and I'm going to do that now. Let's grab this one up. So what we've got then is 0, 2, and then 10, 0. So that's going to look something like so. So let's put that through there. Now, this is going to have to be fairly accurate, because the first method that I'm going to do is by locating integer values given the scale that I've got here. So this is going to have to be fairly accurate. Okay, so let's get that through there. So as before, what we did was label this up. So this one now is x. So x plus 5y is going to be equal to 10. So that's the line I've drawn. Now we want this to be greater than 10, so we need to decide which part we're shading out. Quite clearly it's going to be above the line. If we test 0, 0, 0 plus 0 is not going to be greater than 10, so we're going to shade below the line. So a bit more practice from last time, and we're coming round like so. So let's come down here, and it will be all of this. Now the one down the bottom where I've got x is greater than 0 and y, or greater equal to 0, and y is greater equal to 0, that these two axes account for that constraint. So there we go, that's the first one. And my sketching or shading isn't brilliant, but hopefully it'll give you some idea. So that's the first one sorted. Now let's do the next one. Let's do this one. 3x plus 4y has got to be less or equal to 24. So let's do the second one. So if I now set x to be equal to 0, what we're going to have now is 0, 6. Then if I set y equal to 0, we're going to have 8, 0. So all I'm doing now is simply graphing these. And this is what we looked at before. Okay, so let's do that one. What we've got then is 0680. So 06, that's just there, and then that will be now 80. So let's just put this into place and just straighten it out a bit. Okay, so that looks pretty good. Okay, there we go. So let's now label this up, and remember I'm writing that this is 3x plus 4y is equal to 24. So 3x plus 4y is equal to 24. Now we're interested in the values that are going to be less than that. Quite clearly it's going to be this side of the line, so we're going to shade out the other side. Again, test your point, as we did in the last video, 0, 0. Quite clearly that satisfies this inequality. 3 lots of 0 plus 4 lots of 0 is going to be less than 24. The line is included as it's an inclusive inequality, so let's just put that on, and it will look something give or take like so. So not brilliant. I would like to be more accurate with my shading, but on the computer with this pen it's not the easiest thing in the world. Okay, so let's go ahead and shade that. This will get rid of quite clearly everything above here. Let's do that. If you want to make yourself a cup of tea while I'm doing this, feel free, as it's not the most riveting thing to watch, shading this out. So pencil and ruler if you're doing it yourself. Let's get all of that gone. And then all up here, okay? I'm probably going to be lazy and not do the whole of it. Let's just leave that, okay? And then, of course, it would be all up here as well. Well, I might as well do it while I'm talking about it. So let's get a shot of all of that. So you can see that our feasible region is now shrinking, okay? Feasible region is going to be between those two lines currently. Okay, let's now get the next constraint going on. So the third one that we've got is very similar to the last one. So let's just now set x to be equal to 0. So what we'd have is 0, 8. We will set now y equal to 0. So what's that going to give us? 6, 0. So that's this one here. So I need to draw that line on, and let's draw that one. So let's go ahead. What do we want? We want 0, 8, which is going to be just there. That's 0, 8. And then 6, 0. So through here and then like so. So we want it now to be, let's grab that up, okay. We want it to be now less than that value, so let's do that. Let's just make that like so. That's 8, isn't it? And we'll write this on. So what we're going to have then, this is going to now be 4x plus 3y is equal to 24. We want to know where it's less than that. Quite clearly, it's this side of the line we want. Therefore, we're going to shade out this bit. So let's go ahead and shade that part out. Okay, so let's get rid of all of this, and we've got our values. So if you're not happy with anything we've done so far, this is all been covered in the last couple of videos, so you can go back and watch those. Right, so here we are, fairly accurate. I'm fairly happy with the level of accuracy. Now, what we want to do is have integer values. We're maximising now 3x plus 2y. So when I get now my objective line on here, okay, when we push it out of the feasible region, which is just here, we want the furthest point. Because this particular example gives us a small scale, the first method we can do is to test each of these values. So what I'm going to do is just go through my feasible region and look at all of the integer solutions. So if we consider now that this is going to be 0, 6, that's in there, okay? So that's on the line, that's included. This one is, so 0, 5, 0, 4, 0, 3, and we're going to have now 0, 2. Quite clearly, if we're trying to maximise this, if we've got a choice of 0, 2 or 0, 3, we're going to take 0, 3. Okay? There's another integer solution. There's another one, there's another one, there's another one. So if we look at this one right here, this one is 3, 4. So quite clearly we would have that over 3, 3, and we would have that over 3, 2. We've got one just here, which is going to be 4, 3. We've got the one just here. We've got the one just here. And that now is going to leave us this one just here. So these are our integer solutions. And that's why the level of accuracy is really important. Now, with this particular approach, what we can't really do is have it when we've got a massive scale. So, for example, if this is 1600 and this is 1800 here, it becomes a nightmare. Only because we got the small scale is this working for me. Okay, so let's now look at our objective line. So let's just write here objective line. So for the objective line, okay, is going to give us the following. So we want now 3x plus 2y. So if I set that equal to 6, let's just set that equal to 6, 3x plus 2y. Remember, we can set this to a constant. I can have x is 2 and then y is going to be 3. So let's do that. Let's grab my objective line. So we're going to have the point now 2, 3. And again, this was something we covered before. Right, now if we do this, and again, with your approach in the exam, if you're going to do an objective line, you need to draw this on and then label it up. So let's write this. This is the objective line, so let's just call it P. Let's say it's P, and that's going to be equal to 3x plus 2y. Now, what I'm going to do is now move this through the feasible region. This is the feasible region. If we're going to use this particular approach when we're finding these integer solutions, it's the last integer solution that it passes through. So it's the last integer solution that the objective line passes through as it leaves. That will give us now the maximum values for our decision variables. So let's look at that. Remember, I can't change the gradient of that. If you're doing this, you're going to do it with 2 rulers or a set square and a ruler. So quite clearly it's not that one, it's not those two, it's not these ones, it's not these. And now we get into the business end of things. So if we consider what we're looking at here, we're moving out, and the last one is this one just here. We can see that the last integer solution that this is going to pass through as it's leaving the feasible region is the integer solution, which is going to be 5, 1. So that's down there, that's bang on that line, and it could have possibly been quite easy to miss. So what we're going to do is state now, and I'll just put this in, let's grab up a different colour. What we've got here is this solution here. So what we do, we state using the objective line that we've moved it out and found this as our value. So what we can say then is the optimal, so optimal, and remember this is the optimal integer, okay, and optimal integer values, and I'll write them here. We've got now that x is equal to 5, y is equal to 1, okay? So all I've done is found that there. Remember, we now need to simply sub this in to maximise this. So what we could say then, and I'll say that this is going to be called Pmax, okay? So Pmax, bearing in mind that I've called it P, Pmax is going to be 3 lots of 5, and then we're going to have plus 2 lots of 1. 3 lots of 5 plus 2 lots of 1 is going to give me 17. So the maximum value of now our objective function, which was P is equal to 3x plus 2y, which we're trying to maximise, would have given us that. If we're trying to minimise it, it would be this one just here, as that's the first one as we're going through the feasible region. So there we go. Again, this is quite a nice method if you can see what these are. So that is the first method. It's to define each of the integer solutions that we can see graphically, use the objective line, go through, and it's the final one as you're leaving now the feasible region. Okay, so say we were on a much larger scale right here, what we would do is use the second method. Still have the objective line. Here's our objective line. And what we would do now is go through, and it would be the point, the last point as we're leaving. And you can see now that it would be this vertex here, okay? So what we'd do, we would go through the feasible region. So assume that we didn't just find that point. We would go through, we would check each vertex as we did in the last video, and we would find that the last one as we're leaving the feasible region is the intersection now of these two lines. That's the line here, 4x plus 3y is equal to 24, and now x plus 5y is equal to 10. As before, we're going to set up a simultaneous equation. This, as you can see, is going to give us non-integer solutions. Unless my graph is atrocious, this isn't going to give us integer solutions. So what we can say then now, and I'll call this equation 1, x plus 5y is equal to 10. I'm looking at this point right here, and that's that line. We've also got this line just here, the 4x plus 3y is equal to 24. So equation 2, 4x plus 3y is equal to the 24. So what we're going to do is solve these now, the simultaneous equations, algebraically. Okay, so what can I do with it? I can just multiply the top equation. Let's just multiply equation 1 by 4. So let's just multiply this up by 4, so times it by 4. So equation 1 is going to be 4x plus, now what's that going to give me? 20y is equal to 40. So what's that leave us now? That leaves us 17x is equal to 16. So 17y is equal to 16, just by simply subtracting equation 2 from equation 1. So we've got now 17y is equal to 16, and y is equal to 16 over 17. So, quite clearly, that is not now an integer solution. Okay, what we can now do is find the value of y. So let's go ahead and do that. We can put it into, find the value of x. So we can say, using the top one, x is going to be equal to 10 minus 5 lots of y, which is going to be minus 80 over 17. Okay, so what's that going to give me? 90 over 17. Let's just do that. Looks good. So x is going to be equal to 90 over 17. If I just multiply that up, that's 170 minus 80 is 90. So 90 over 17. Right, so these are now our fractional answers. And if you were just asked for the optimal value of the decision variables, remember, it's not the optimal or optimum value of the objective function. These are just the values that will give us that. Now, what we do here is the following. And the way I like to do this is to simply now draw a little grid, okay? In your exam, you might want to show that you're plugging these values in, and I strongly suggest that you're plugging your values into each of these inequalities. And you could do that by drawing a little table. If you wanted, let's do a table rather than talking about this. Let's actually do it. Okay, so what I'm going to do is the following. And we'll put that just there. We'll put that just there, and we'll put that just there. Okay, this isn't ideal, but it will give you some idea of how you can do this. What we're going to do is consider now integer solutions around these two values. So let's look at the first one. Let's grab this up. Okay, so what I'm going to have now is the following point. Let's just grab a calculator up. So 90 over 17. Okay, so 90 divided by 17. That's going to give me, what's that going to be, 5.29. Quite clearly, this is going to give us now just under 1. So, my combinations of integer solutions around this, if we say now that x is approximately 5.29, approximately 5.3, and y is is just under 1. So, let's just put this, 16 over 17. Let's write that in. So what are we going to get? 0.94. So what we do here is now consider the integer solutions around here. And the first one would be the lower bound of each. So what we'd have is 0.5. Okay, so that's an integer solution around there. Okay, so what we'd have is now on here, 5,0, other way around. Let's just change that over, 5,0. Okay, so let's do that. So we're going to have 5,0. Okay, if we now consider the lower bound of this one and the upper bound of that one, we're going to have 5,1. Okay, if we consider the upper bound of this, and when I'm talking about upper bound, I'm talking about rounding up as an integer. Maybe upper bound is not the ideal terminology, but hopefully that makes some sense. So 6 and 0, and then we would have now 6 and 1. What we need to do is consider now these constraints, okay? First one, x plus 5y is greater than 10. And you might, again, let's just move these along. Let's just give ourselves a bit more space. So x plus 5y, is x plus 5y greater than 10? Now, we can see from this the ones that aren't going to be included. But I'm kind of almost pretending that we can't see that. And we're just going to do this by subbing the values in. So on the first one, what we've got now is x plus 5y is greater than 10. So let's just put this here. So x plus 5y, is this going to be greater or equal to 10? So let's look at this now. X plus 5y, is that going to be greater or equal to 10? The answer is no, because 5 plus 0 is not greater than 10. Okay, this one right here, is 5 plus 5 lots of 1 10 or more? Quite clearly it is. Is this one 6 plus 5 lots of naught? No, so that is no good either. And then this one quite clearly will give us 11, so that's good to go. Now, this leaves us these two to consider, and the more of these inequalities you do, the better or the easier it is to do it. So let's look at the next one. Again, ignore this for now. You can kind of see what we're aiming at. 3x plus 4y is less than 24. So 3x plus 4y is less or equal to 24. So we're only now considering these ones. So 3 lots of 5 is 15, so that's going to give me 19, so that's still good to go. Okay, this one, 3 lots of 6 is 18, plus now 4 lots of 1, that's still going to be less. So again, we've still got both of these in the running. If we now look at the next constraint, 4x plus 3y, so 4x plus 3y has to be less or equal to 24. So let's have a go at this one. Well, that's going to give me 23. 4 lots of 5 plus 3 is going to give me, so that works. If we look at this one though, that's going to give me 24 plus 3, 27. So that falls foul. I mean, the x is greater than 0, y is greater than 0. Quite clearly all of these satisfy, and you might want to put it there. So what we can see from this now is that the one that satisfies this, and let's just go across here, it's this one right here, okay? It satisfies all of the inequalities that we want or need to satisfy because remember, we're maximising subject to these constraints. So all we would do is go ahead and pick this one right here. So what we're going to have then is 5, 1. So let's go for that. And then we would simply write now P max. So P max going back now to the objective. We've got now 3. Remember, this was now, so P was 3x plus 2y. And we wanted now, so what have we got? We've got the 5 one. So we've got 3 lots of 5. Plus 2 lots of 1. Quite clearly, again, we're going to get 17 from that. So there we go, 2 different methods. If you can see this now, with your objective line, it is the last integer value as you're passing out of a feasible region. That's assuming that you want the maximum. The other way around, if you wanted the minimum, then you would go this way. But we can see that's going to be just here. So that's the idea. All you're doing is either testing these integer solutions, which is easy when you've got low numbers, or you're looking now at the intersection of the 2 lines where your vertex is. So in this particular case, it's this one, as that's a maximum. You're solving algebraically a simultaneous equation, and you're considering integer values around these. So 5 0, 5 1, 6 0, and 6 1. As if we round this up, we've got 6. If we round it down, we've got 5. If we round this down, we've got 0. If we round it up, we get 1. In terms of your table here, I would probably suggest putting the values and then having a column here to say, is this in the region? So if you want, calculate these. I've just put a tick to save me working all of these out, but as you can see, they're fairly straightforward. Now, if you want to work them out, to simply sub them in. But you might want to, again, put the values in and then say, is it in the region? Yes, it is. No, it's not. No, it's not. No, it's not. So there we go. That's a feasible region. We solved, we plugged it in, and that is one way in which we can get now the optimal solution to the linear programming problem where we've got this additional constraint that we have to have integer values.